Great. So, colleagues, welcome to the second subsession of Environmental Impacts of War. I am Dr. Brian Lintott, and I have the great pleasure and privilege of working with a range of colleagues on the Tirpitz site project. I was thinking I would read a list, but I realized that would take up the whole 5 minutes because we have so many wonderful colleagues. But you will see them acknowledged online, and I would like to acknowledge them now. In addition, I would like to say thank you to Dr. Juliana Bockveld from the Norwegian Naval Museum, who gave a very informative and interesting lecture yesterday about the post-World War II interpretive history and subsequent different complex meanings of the Tirpitz. In this particular session, we are focusing on the biological side of things, and then later the radiological. And one of the things that has greatly informed the Tirpitz project is engaging with the Remarco project. And it is my great pleasure and privilege to invite my two colleagues onto the stage. So Matthias and Jens, could you please introduce yourself and discuss and inform our audience about Remarco? Thank you.
Jens, would you introduce you?
Yeah. Okay, welcome everybody. Thank you for coming to listen to us. My name is Jens Sternheim. I'm from Germany, and I worked for 20 years with sea dump munition and the problems related to that. Willst du dich auch vorstellen?
Yeah, my name is Matthias Brenner. I'm a marine biologist from the Alfred Wegener Institute. I'm involved, or I'm interested in what happens if organisms come into contact with the toxic compounds of leaking munitions. I'm doing that for the last 12, 13 years in different projects, both in the Baltic Sea and in the North Sea, and currently we are coordinating the Remarco project, and this is the connection to Brian, because he is now at advisory board, and so he invited us to come here to Tromsø and maybe also joint work at the Tirpitz site during our project. Thank you.
Okay. In roughly 20 years ago, the public in Germany was a little bit raised to the munition dumped in the sea. We had some accidents, we had some occasions on the beach where we have washed ashore explosive stuff, and that creates a real problem for our government. And so they tasked me to find a way how to get rid of this problem, or at least manage the problem. That leads us to a group of experts. It's growing over the years, and 2011, till 2011, we aggregated a report, and it's 1,100 pages thick. And mostly outcome of this report was that we don't know nothing. Or at least not enough, but we suspected that the chemical compounds in the munition will release to the seawater due to corrosion. So, in preparing this report, we searched archives and defined a lot of dumping grounds in the German waters. Roughly, we estimated 1.6 million tons of dump munition only in German waters. So from that time, we know that we have to act. And there are some milestones from the process. What I tried to do was figure out, I was leading this group, and I tried to figure out a kind of process, how to deal with it. And that was the beginning of a lot of national and international projects that we conducted. It's 23 million euro since 2005 we put in that, and the ongoing process says 30 million euro 2019. When I stopped working, I'm retired now, The federal government gave us 100 million to work on this project, and so I give over to Matthias at this point, and he will lead you to the future.
Yeah, as Jens explained, so within the last 5 years, we got another 30 million for different national and international projects. Now, by far the most, or more projects are conducted in the Baltic Sea area. You see on the upper side, are 6 ongoing projects in the Baltic Sea. However, in the last 5 years, only 3 projects were funded in the North Sea, and the only ongoing project is the already mentioned Remarco project. So this is sort of a transfer area of knowledge is the North Sea, because most of the knowledge is generated in the Baltic Sea. However, this is a small community still, even if it's international projects. We know each other. We are sometimes already partner in some of the Baltic Sea projects, leading the North Sea projects, so we know each other, and so the work is not really not redundant or something like that. We closely cooperate with each other. Yes, what did we do in all those projects? So basically you can divide that in 3 fields. So it is basic research, proving that there is leakage, inventing analytical methods to get evidence that there is concentration in the water, in the sediments, in the organisms, that the organisms can take up this contamination and it had effects on the organisms. And all the project, this is a speciality of our approaches. There's always the involvement of relevant stakeholders. So administration was in the advisory board, decision makers from policy were in the advisory board, NGOs and so forth and so on. And we just don't want only to describe the problem, we wanted also to provide solutions, both to our stakeholders, that we have, for example, best practice guides, that we have an accessible database for all our results, that we have provided monitoring concept and help them with decision support tools or risk assessment tools. And also, we provide monitoring concepts, we work on robotics for remediation and the force and so on. So coming back to the North Sea, as I said, I explained that the North Sea is sort of a transfer region for knowledge obtained in the Baltic Sea. Why is that so? Now, in the North Sea is much more munition dumped than in the Baltic Sea. 1.3 million tons are remained in the Baltic Sea, and especially in the German Bight. Now, small places where hundreds of thousands of tons are lying. So, for example, north of the island of Spiekeroog, several 100,000 tons. Then in the Jade estuary, down there, it's also a place with several 100,000 tons of munitions. However, this is buried under several meters of sediments. Now, due to natural processes north of Spiekeroog, for example, and due to sediment dumpings from the harbor of Wilhelmshaven in the Jade estuary. So it's really hard to access this munition, because in contrast, in the Baltic Sea, it's all lying on the sediment. You can see those munitions. You can easily map those munitions. You can see the statues of munition. So this is by far more difficult in the Baltic Sea. That's why we are a bit behind with our research in the North Sea than in the Baltic Sea, and that's why we actually looked at the wrecks first, the warship wrecks in the North Sea, because they are not silted up, and they have, of course, then an effect and directly in contact with the surrounding water. So there you can measure effects around the point sources of the dissolved explosive but this is hardly possible at the dumping sites. So, and we did also quite a lot within this project regarding public outreach. However, we had, as I said, all our stakeholders in our consortium, so they knew already what was coming up in the press when we contacted press and did public outreach. However, it created a sort of pressure also of our decision makers to act on this topic, and this was quite successful. That was Jens already explained, because last year our government decided that we get 100 million euros to start the first remediation program of dumped munition. This is the first situation in the world. Otherwise, you have only emergency response to munition. This was the first time that dumped munition was remediated. professionally in a pilot study done in the Baltic Sea. And the vision is then that in the upcoming years, platforms will be installed right next to the dumping sites, and the stuff will be remediated on site next to the dumping grounds. And I would say our scientific results, the pressure from the media, and also the interest of the industry to take this also dump munition as a business case brought us to the point where we are at the moment. And I would like to invite you just to approach us, because as I told you, many experience are there already, and some of them might be useful also for you if you plan projects. If you want to approach munitions in your waters, please contact us. Maybe we can show you already some results which could work as a basis for you to start your own projects in the region and to tackle the munition problem also, for example, in this Arctic region. Yes, and with that I say thank you. We say thank you very much.
And we do have time for 2 or 3 questions. So if you could please wait for the microphone to come to you.
Thank you so much for your talk. I'm just curious what the expected environmental impacts of the remediation technology, the platforms, and all the various equipment that will be necessary for that work to be carried out.
This is actually a long answer to this question. So we are trying to figure out what is necessary. So we had this pilot, as I said, already this summer in the Baltic Sea, in Lübeck Bay. And so we get an estimation of what is needed and what is already there. And there is already quite a lot there, because we have specialized companies now able to do remediation, but they did it offshore for the offshore industry right now. And of course, this is different regarding these dumping sites, because you have piles of all kind of munition lying around there. But I guess we have, after this program finished, we have a quite good idea of how it can be done, what's already there, what's still needed, and also a bit of a price, what that will be cost, what that would cost now.
Maybe I can add one idea. From the beginning, when we started this systematic approach to get an idea how we deal with ammunition, we involved the German NGOs, the big ones, from Greenpeace to NABU and so on and so on and so on. And they were also on our projects, and they had the chance to bring their ideas into this, and that creates a kind of trust between us. So we know that it's a problem, but we do it hopefully with the least impact on the nature. So.
It's on? Yeah, just to add to this question. So I'm from Kiel, and we do the combined monitoring during this SOFORT program. So we have sediment water samples and also some biota. We analyze them, and we do not find any significant enhancement of the concentrations of these munition chemicals down there in these samples, which were moved then around these dumping sites. Thanks.
Yeah. But we're taking care of that.
Yes, there is one more question, please.
Hi, could you tell us just a bit about the design process of the remediation platforms and what appear to be the grabs or the arms that you're using to move the munitions?
Well, we have some underwater devices now collecting. It shall be all now based on robotics, so no diving and so on. So a selection on the ground. We have intermediate wet storages where identified and munition is stored. And so far, it's now during this pilot, it was brought then back to land and was then remediated in our land-based system. And the future system would be that it's then taken up to this platform, fully delaborated first, and finally burned on the platform. So this is the concept. However, this is still PowerPoint. No.
It's under construction right now.
So disposal is on the platform?
Yeah. Full delaboration process, including disposal and final burning.
Yeah, it should be operational next year. It's a plan.
Don't promise too much.
No,
Thank you so much. That is brilliant. Well done. So the next presentation is by Dr. Sven Bergmann, a senior researcher and curator at the German Maritime Museum, Leibniz Institute for Maritime History. At the Institute, he coordinates exhibitions, including one from North Sea Rex, which was very, very successful. And his research areas are ships and the environment. He's trained as a cultural anthropologist and STS researcher. And if I could invite Sven now to join us digitally. Welcome.
Yeah, hello. Thanks, Brian, for having me here at this conference. My problem is I cannot share the screen at the moment because you have to give me the permission to do that. So if you want to see my slides, I cannot see you anymore. I see me double. Someone has to give me the permission.
Just while this is being resolved, would you be so kind as to tell us about the touring exhibition for a minute or two? And we can give you extra time for your speech.
It's very strange for me because I see my face double here on the screen and I don't see any one of you. So it's a bit strange experience for me. I have no feeling that I'm talking at the conference at the moment. So, but if you can hear me, okay, I can do that. I mean, I can say mostly what is, yeah. Okay, now I see another screen. Okay, yeah, I mean, our role, many people might have asked the German Maritime Museum what has it to do with these projects, and we had been quite active in both of the projects. So it was first in the former NSW project, the North Sea Rex project from 2018 to 2023, and after that now in the new Remarco project, and yeah, mostly. And I really would like to show you the slides, but I do not know.
We can currently see your slide. Could you please just say next slide, and we can
Okay, you have you're doing with C slide. Okay, yeah, okay. Then next slide, please. Yes, I did already. Yeah, next slide, please. Yeah, this was our main issue in the first project. Beneath a lot of communication and so on. We did a traveling exhibition during the project that was already finished in 2021, so midterm of the project, and we toured with this traveling exhibition through 5 countries, from Belgium to Norway, where our project partner were, and also some more places in Germany. And you still can visit the traveling exhibition online on this web address I have there, and we also have some part of it is also integrated in the German Maritime Museum in Bremerhaven in Germany now. So next slide, please. Yeah, I'm not as the others in the sessions from the natural sciences, and to do this interdisciplinary or transdisciplinary work together with the dominance of natural scientists or engineers is always a bit challenging, because I think we have to understand that different epistemic cultures are involved here, like you. And I mean, it's good that is good tackled in this comic you see on the other side, where the one is asking why. We all, the national scientists, are asking why we have all that knowledge line and just we have to apply it to society. So, and then the social scientist comes in and says, oh, that is a rather complex issue, because society isn't just any variable, but it's a rather tricky process. And these things, I think, are always very challenging. Like, I mean, it's also a bit generalizing here on the slide, but like if you dive between university and particularity or evidence and experience and all the other issues, it always is a bit challenging to do so. And I will come to it a bit more concretely. Next slide, please. Yeah, like also these different epistemic languages. I mean, in the North Sea project, we focused mostly on risk, and there's a lot of debate in the social sciences about risk. There has also been risk theory was a lot in the 90s. Nowadays, me and my college are moving much more to terms like uncertainty, because with uncertainty, it's a bit a term. It reminds me sometimes when journalists ask me about. I was very often asked in the formal project, can we eat the fish now? And I mean, if you were asked that question regarding fish in the North Sea, it's always a bit like I was not laughing at the journalist, but I was in myself. I was a bit laughing because I mean, if you look at the North Sea as a technosphere, that an ocean that is not already untouched anymore since the 20th century or the Anthropocene, and is also a technochemical experiment where dilute acid, nutrients, metals, everything went in, and also TNT. So this question is, I mean, this question is also based in this uncertainty. And my own research, I always tried to tackle this with the term what I call speculative ecology. So ecologies, we have a lot of chemical intervention in the ocean, but with some things we know what will happen, but with some things we do not know exactly what will happen with ecosystems, like in 30, 40, 50 years. So this speculation is also for me very intriguing. Next slide, please. Okay. I can't read with this method. I can't read my own slides, but okay, I think I know what it is on then. And this slide is about slow disaster and slow violence, and this is, I think, also when it comes to munition regarding to like fast disasters, like an oil spill or so. It's we regard it also as a slow disaster. Slow disaster means, I mean, when we think about ocean munition, that comes mostly from World War I and World War II. This is over 100 or over 80 years over, but still, due to corrosion and to leakages, TNT and other chemicals go out in the sea and cause a problem. So they cause a problem in the present, and they will cause a problem, a much more severe problem, because we will have more corrosion in the future. So that is this slow violence is something that is has a very large temporality, and but it's not like a fast disaster where you see dead fish on the surface of the sea. So it's not so easy to get people to interest them for slow disasters. Regarding fast disasters are much more evident. Next slide, please. Yeah, and regarding our input in the first project, or the North Sea Rex project with the traveling exhibition, at the moment we are thinking a lot about this kind of participation, about is it public awareness and community outreach? We have to much more think about them. I mean, it had a lot of good effects, like in the terms of rewilding, we from matters of fact we transferred it to matters of concern. It became an issue, something people are concerned about, and we see that what Jens and Matthias, we see it that the solutions come up in Germany, and so. However, we think we also wanted to do another step, so from concern to care, because it's different if people are concerned for something or if they really care about something. So in the Remarco project, we tried to do that at the moment more with ethnographic research in coastal communities on the North Sea. And we are thinking about participation issues with new issues like hybrid forums, or also with citizen science to integrate citizens, the human aspect more. Okay, next slide. This is also my last slide. And coming a bit back to the call of for this panel, for the conference, so the past, the present, and the future. So when we look now from our time on the past, so mostly the munition dumping after the two world wars, we can see it now as a failed waste management plant. So containment or enclosure, this was failed because we know due to corrosion and leakage, the present effects are these items are very unruly and not so easy to manage. And so we are at the moment much into solution seeking. Also, we know that the ocean is not as robust as it was seen in the first area of industrialization. We know now that also the ocean is vulnerable, and I think this caring for the more than human, that is the ocean in this aspect, and its species that lives there, is also an endeavor to do much more collaborative research focused on futures, together with colleagues from policy, from governance, from the marine natural sciences and engineers, and so I hopefully that we will have some discussion about that on this conference. Last slide, please. Yeah, and here's my email address, because I think we do not have so much time for discussion here at this session. So thank you very much.
Sven, thank you for an excellent presentation. We hope to have a few minutes at the end of this session, so please do stay online. And I would encourage colleagues to get in contact with Sven with any questions. Very responsive, very informative, very insightful. Thank you once again. Our next talk is by Tobias Boning, and it is World War wrecks as a point source of contamination of the marine environment with energetic compounds. The Vorpostenboot 1302, John Mahn, and Tobias has a background in chemistry and is currently working at the Institute of Toxicology and Pharmacology for Natural Scientists at the University Medical School, Schleswig-Holstein. Are you with us, Tobias?
Good afternoon.
Great. You have the Zoom room.
I think I have the same problem as Sven. I cannot share my screen because the host has deactivated the screen sharing. Okay. Good. Good afternoon. So we can do it this way, and I will say next slide as well. Yes, I'm from the Institute of Toxicology, from the group of Professor Edmund Maser, who will have the talk after myself. And I would like to present you some of the results from the NSW project. And in this case, especially the first wreck that we examined. And this was the German Vorpostenboot 1302. And as we call it, John Mahn. Next slide, please. As you can see, the John Mahn was a civilian fishing trawler that was built in 1927. And with the beginning of the Second World War, it was requisitioned by the German Navy to become an auxiliary warship, a so-called Vorpostenboot. And it was refitted with a variety of anti-aircraft weapons as well as some depth charges, and was integrated into the 13th Vorposten Flotille, 1st 13th Auxiliary Fleet in Rotterdam. Next slide, please. It was used during the Operation Cerberus. This was the transfer of 3 German warships from Brest to the North Sea through the English Channel, and the Vorpostenboot 1302 was used as an outpost boat. And during that operation, it was attacked together with his sister ship, the 1303, the Freiburg, another Vorpostenboot, and was attacked by British bombers and bombed and sunken during this operation. During this attack, the Vorpostenboot was not able to fire any of its ammunitions and sank with approximately 1 ton of explosive material. The main part of this were 10 depth charges, but as well 100 rounds of 88 millimeter artillery and 3,000 rounds of 3.7 centimeter anti-aircraft guns. Today the wreck lies before the coast of Belgium, in the Belgian part of the North Sea, and is in relatively shallow water, what made it interesting for examination during the North Sea Wrecks project. Next slide, please. So you might ask yourself, why does a toxicological institute from a university medical center is interested in explosives and war wrecks? And the answer is nitroaromatic explosives are well known to be toxic to humans with a variety of acute effects as well as chronic effects like mutagenicity and carcinogenity. And it is also known to be toxic to the marine environment, to mussels, to crustaceans, and to fish. And it is discussed whether these nitroaromatic compounds enter the food chain and accumulate in organisms. You can see 4 of these nitroaromatics on the left side, and the main compound that we are focused on is trinitrotoluene, as well as its metabolites 2-ADNT and 4-ADNT, which are similarly dangerous as the parent substance. Next slide, please. Together with our colleagues from the Vlaams Institute for the Sea in Belgium and from the Alfred Wegener Institute, we did a sampling scheme on this wreck. We took some water samples as well as sediment samples in a cross-section around the wreck, and also mussels and passive samplers were placed on the wreck for monitoring. The monitoring period was from March to July 2020, and also fish was caught pouting by fishing with rod. Next slide, please. First, we examined the water samples. We did it by using gas chromatography triple quadrupole mass spectrometry in our institute in Kiel. And we found not only the TNT in the water, but also the metabolites and 1.3 dinitrobenzene. And concentrations were around up to 15 nanogram per liter, which is not really high, but definitely increased to what we normally see in the North Sea, which is below 1 nanogram per liter. Next slide, please. We also analyzed the sediment samples and could detect these energetic compounds at all 12 sampling sites around the wreck. Therefore, there is some spatial distribution of these energetic compounds around the wreck in the water and on the seafloor. Next slide, please. In our mussels, we could also detect not only the metabolites, but also TNT and dinitrobenzene. And in the passive samplers, this substance also were detected. Next slide, please. For the fish, which are especially interesting for research because fish is eaten and plays a much larger role in human diet as mussels usually do. And we examined bile and fillet and could detect small quantities of the metabolites in the bile, but the bile is not eaten by humans. But we could also detect traces of the trinitrotoluene as well as of the metabolites in the fillet in quantities up to 12 nanogram per gram dry weight. And this is especially interesting because the fillet is eaten, and as you can see, the energetic compounds from the wrecks seem to have entered the food chain and are now detectable in the fish around these wreck. Next slide, please. So in total, this Four-Posten-Boot 1302 was the study was a huge success because we could prove that even with a relatively low total explosive mass on the wreck, it acts as a point source for explosive compound pollution in the surrounding water, not only in the water and sediment, but also in biota and in the fish. And this is definitely a problem. And the North Sea not only contains a few wrecks, but over 1,000 raw wrecks with variable amounts of munition on board, and with with the corrosion from the water, the problem of munition release from war wrecks will also exacerbate in the future. This leads to our conclusion that war wrecks should be assessed and monitored for their environmental hazard, not only for the munition, but also for other dangerous components like the oil, the fuel oil or coal in the wrecks. And yeah, this was my conclusion. Thank you for your attention. And are there any questions? Sorry. We also published a publication about this paper about this wreck 2 years ago, and you can see the DOE on this last slide. Thank you. Questions?
Thank you for an excellent presentation, and ask, is it possible for you to wait another 20 minutes for questions, and then we can bundle the Remarco questions together? Brilliant. Thank you so much. So our next presentation is on the topic of how contaminated is our fish with munition chemicals from World War relics. This is by Professor Edmund Mauser, both Professor and Director of the Institute of Toxicology at the University Medical School in Kiel, Germany. His research focuses on human toxicology from a range of different sources, and he is specifically interested in using the blue mussel as a bioindicator. He is involved in several national and international projects and has authored more than 225 scientific publications and reviews. Pleasure.
Thank you. Thank you very much. Can you hear me? Yeah, okay. Thank you very much for this very kind introduction. So in fact, I continue then now the story a little bit from my PhD student, Toby, which he has done very good. So the question is, how contaminated is our fish with munition chemicals from World War relics? And I will focus on the fish especially because, as Toby already said, this fish is eaten by human fish consumers. And we already saw this picture here. And as I'm from the University Medical School, so I'm both interested in human toxicology and also in environmental toxicology. And therefore, we are concerned about the mutagenicity and about the cancerogenicity of this explosive stuff there, and also, of course, on the ecotoxicity. So as Brian already mentioned, we have lots of projects in the last 15 years, and I would focus on the North Sea wreck project, on the Remarco project first, and then give a short glance on the Tattoo project. Just to keep you online, the North Sea here, and it is known that we have more than 10,000 wrecks in the North Sea, and more than 500 are just filled with munition. They sank with munition on board. And with a historian, we were in this NSW project or the Remarco project looking on historical issues, then just to select the right wrecks on this, and including these flagships. There are also some submarines, and we already heard from Tobias the story of the John Mahn. This is the civilian name, which was then the Four-Posten-Boot to protect some specific areas there in the marine environment. So this is the John Mahn we sank in 1942, and we heard that it is now lying on the ground. It was filled with almost 1 metric ton of explosive stuff, both in grenades or in bombs and deep depth charges. Then it is now lying there on the ground. It is corroding, and also the ammunition is corroding, and this is a big deal with the leakage there. And Toby already told that we are investigating waters, the sediment, the mussels, and also the fish. And I would like to focus on the fish, because the fish is then eaten by humans. And just starting with the John Mahon, this picture you have already seen. We do not eat bile, but we do eat the fillet, and therefore I will later come back to a risk calculation, to the daily business of a toxicologist, to make a risk calculation to answer the question if the fish could be eaten or could not be eaten. So this is another wreck which we are investigating. This is a submarine, this is UC-30 here, and also I focus here on the fish fillet. Also we have water and sediment samples there. And you see that we have 42 individual fish samples, and they are all except one in the order of just 2 nanogram per gram dry weight of fillet. And next is then the SMS mines. Also here we have lots of data, but we focus on the fish fillet, and also here we have something. These were 40 fishes, 2 nanogram per gram dry weight. And then we have the Ariadne. Here we have higher concentrations, and we will hear it about from Romina. She will go more into detail, I guess. So here we have on the Ariadne higher concentrations, and we end up with some 4 to 5 nanogram per gram dry weight. So this are the North Sea wrecks. In another project from the Umweltbundesamt, we were focusing on the Ostfriesische Inseln here in north of Germany there, and we caught there flatfish. So, and the flatfish, this was then on the island Borkum, on the island Baltrum, and on the Außenweser. And we heard from Matthias that there are several 10,000 tons of munition dumped here in this area. So we could expect that the fish is also contaminated with munition compounds. So this is the barks here are then the bile, different concentrations of TNT or the metabolites of TNT. So the concentrations in bile are 0.10, 0.1, 0.2. So this is very tiny concentrations. But when we then look at the fillets of these fish, so Borkum, Baltrum, and Außenweser, we see that we have the mother compound, the TNT itself, in the 4 nanogram per gram region. And this is something which should be considered from the toxicological point of view, and therefore I just focus now on the risk calculation. This is the daily business of a toxicologist, just to infer, can we eat the fish or can we not, is this fish not be eaten? So there are only 2 carcinogenicity studies in the past done by Foredi et al. In 1984, and it turned out that rats had a sensitive endpoint with lymphoma and bladder cancer by being fed with 50 milligram per kilogram body weight with TNT, while mice were far more sensitive. They already get bladder cancer and lymphoma at a concentration of 1.5 milligram per kilogram body weight. So, and this is then just calculated to infer if humans, what about the humans then? Because there are only 2 studies in the past, we have a safety factor of 25,000. So this value here of 1.5 milligram per kilogram is divided by 25,000, and we end up then with 60 nanogram per kilogram body weight. And just thinking about a human being is 60 kilograms, something like that, we can then calculate that a human being can eat 3.6 microgram TNT per day without getting bladder cancer or lymphoma. So what does this mean for the fish? This is the John Mahon fish, the pouting, which we heard about. So to make a long story short, I need 1 semester to teach this to my students, this calculation. So the consumption of this fish is okay, which we find at the wreck. So you can even eat 500 gram fish per day on a daily basis, lifelong. So And this is the chance to have 500 gram fish per day, especially from this wreck, is very minor, so we can say this fish is safe. And when it comes to the fish which we caught then in the Ostfriesische Inseln, we can even eat 700 gram fish per day on a lifelong basis. So also here you can say at the moment fish is safe. What do I mean with moment? So I leave now the fish and I do come to mussels. So also the title of my talk is Fish. I have a very interesting slide related to mussels. This was a project financed by the Umweltbundesamt, and we had a chance to look on a time series what is the entrance of munition compounds into biota. And this Umweltprobenbank, this is a facility, the Human Environmental Specimen Bank. They collect several samples starting in '85. So we were lucky to get from them mussel samples starting from '85. Every year we got samples until 2021. And what we see is very interesting, because until the year 2000 we do not see any sign of TNT or TNT metabolites in these mussels. But then starting in 2001 and 2, so we have slightly increasing and then even very clearly increase in contamination of these mussels with munition chemicals. What does this tell us? So this is a very convincing picture for politicians, just to urge them to do something and to start a remediation. Because when we follow this line, yeah, maybe we end up somewhere in 20, 30, 40 years at concentrations which might really harm human beings when they eat mussels or when they eat fish. So, and this is, I think, a convincing table to speed up. And this leads me then to my conclusion. So the World War relicts, they emerge as a new group of pollutants, worldwide oceans. Tobias Bühning already mentioned that we have, of course, a whole cocktail of contaminants, starting from microplastics, pesticides, pharmaceuticals, and now we have the new chemicals from the World War also coming into this field and contaminating our oceans then. So we know that the explosive chemicals are toxic and carcinogenic. This is done by carcinogenesis studies and by aquarium studies. And currently there's no acute risk when we see the concentrations that we find in the fish. But if corrosion continues, then we might end up at higher concentrations in fish and other biota or other seafood. And then it might happen that the humans are affected when they eat contaminated marine food. So what we see, and which I couldn't present here because of time reasons, we already see that mussels suffer from oxidative stress. So we developed a molecular biomarker, and we see that mussels living near dump sites or living at the wreck, they show signs of oxidative stress. And this is some of the first indications that we have already an endangerment of the ecology and diversity of the ecology, the marine ecology. So, as already we heard, dumping, a recovery of dumped munitions or even wrecks should begin, and we should work on this because we today have the technology and some money to start from the German government, as we heard from Matthias and Jens. So, thank you for your attention.
An excellent presentation, and as somebody said, the time to plant a tree was yesterday. So there is a matter of some urgency here. Our next speaker is going to be, excuse me, a brief moment, Romina Schuster. And please note there is a slight change to the program. Romina has very kindly agreed to do her 2 talks, one after another, and then we will have the 2 radionuclide talks together. Romina works at Alfred Wegener Institute and is a PhD candidate at the University of Bremen. Thank you. Please come on.
Yeah, thank you for your kind introduction. Basically, I'm just going to continue the presentations before from Tobias and Edmund, but I'm focusing on the health of marine organisms. So I prepared 2 different presentations and I'm now trying to combine them somehow, so I might be able to save some time for discussion afterwards. But the first part is about the health of blue mussels, and the second part is about the health of fish. So I'm not going to repeat everything that was said before, because it might be a bit boring, but I'm going to give you just a teeny tiny bit of background information. So during my PhD, we focused on the on TNT as an explosive compound, basically because it was the most used explosive compound in the Second World War, with insanely high amounts of production rates, and therefore after the World War we did dump insanely high amounts in the North and Baltic Sea. It is stable over long periods of time, so even after decades there's still a toxicity and a threat to the environment, and it is toxic to the environment and to humans, and therefore it is necessary to investigate the effects of these compounds. And then, as Matthias and Jens mentioned before, we do have more than 1 million tons of conventional munition dumped in the North Sea, but most of the munition was dumped in dumping sites and is covered in sediment, so it might be a bit of a problem to actually investigate the biological effects. But we do have another problem. The North Sea is a graveyard of several hundred shipwrecks, and those are not covered, and we do see that there's munition either lying next to the wrecks or still on the wrecks. So we can use those wrecks to give some information about the problem at hand. And for the mussel experiments, we chose 3 different wrecks from the First and Second World War. We have the KW58, this one, it's in front of Belgium. We do have the, which sank during the Second World War. We have the SMS Mainz, which is this one. It sank during the First War at the Battle of Heligoland, and the submarine UC-30 in front of Denmark, and those which also sank during the First World War. All those wrecks have different amounts of ammunition still left on the wrecks. So we might be able to use those amounts to actually see if there's an effect based on the amount left on the wrecks. And we do know there are different organisms living in the North Sea, and we need specific criteria to choose an organism to be able to give information about the situation, and therefore we choose the blue mussels because they are stationary, so we can use them to give actually information about one specific area. They are filter-feeding organisms, so they do filter large amounts of water and therefore also filter large amounts of pollutant diluted in the water. And what we did to investigate the health of those animals, we choose a multi-biomarker approach because pollutants affect an organism on different levels. So even after a short period of time, and even if we have only low concentrations, we can actually see the first effects on the lower level of organisms. So we choose enzymes, for example, the catalase and glutathione S-transferase, and metabolic end products, lipofuscin and neutral lipids. I'm going to tell you later what they're doing, so just what we did. And then on those 3 wrecks, we developed those metal cages filled with mussels, either directly on the wreck, as we did on the UC-30, so we put those wrecks, those cages directly at mine wells on the wreck, or at the SMS Mainz and the KW58, we attach those cages to landers and then put those landers next to the wrecks. And then we left them in the water for several weeks, up to 8 weeks after those exposure time. Divers went down to the wrecks, got the mussels back, and we either dissected them directly after we retrieved them on the on a research vessel, or once we came back to shore, and then tried to dissect them as soon as possible. And then I can already give you some results. So before I start with my results, I just want to tell you those numbers are just up to, so those are like the highest amounts of TNT measured in the water and the sediment, kindly done by our colleagues from Kiel, from the UKSH. And I'm going to tell you a bit about the enzyme activity. So both enzymes are part of the antioxidant defense system. Catalase is more important for oxidative stress, and glutathione S transferase GST is also part of the detoxification of xenobiotics. So what we can see in both enzymes, but especially in catalase, we do have a downregulation of the enzyme activity in RECs with the higher values, especially in the sediment and in the water. It's kind of the same for the GST, but especially the submarine UC30 and the SMS mites, there's not too much difference. I'm going to show you another result later where it might be able to explain these results, because one would think that the pollutant in the water might lead to an increasing enzyme activity, but there might be an explanation why it looks like this. But we also have metabolic end products, lipofuscin and nitrolipids. Both show oxidative stress in an organism. And here we can see quite the opposite from the enzyme activity. So we do see an increasing accumulation of metabolic end products in mussels we retrieve from the wrecks with the higher concentrations. And then we might be able to explain the enzyme activity. Detoxification needs energy. So it does take energy to start some of the mechanisms, and glycogen is the primary energy source for mussels. And so we can see that we do have a lower amount of glycogen in the mussels we retrieve from the wrecks with the higher concentrations in the water and in the sediment, and therefore there might not be enough energy to be able to still work with the enzyme activity and to still be able to detoxificate the organism. I might be able to skip over this one, over the conclusion and the summary, because I'm going to give the second talk and it's basically the same summary and conclusion. So I'm just going to skip this one. Yes.
That was a preview.
Yes.
Brilliant. So how long have you been working on this for now?
3 years. Yes. So I'm just going to continue, and now I'm going to show you the results we got from the common depth in the North Sea. Therefore, I don't need background information because I basically just gave all the background information, but I just want to mention that we switched some of the wrecks. So we got rid of the KW58 in Belgium, and then we added the SMS Ariadne, which also sunk during the Battle of Heligoland. And we also added a reference area at the island of Borkum. It's the same biomarker approach, so I don't need to explain this one again, but there is a big positive thing about working with fish, because some diseases do take time to develop. So it does take months or even years to develop those diseases, and therefore we can use fish, which live up to several years, to use them as an indicator of those long-time diseases. And we used fish for liver alterations and the lysosomal membrane stability. But fish are actually not stationary, well, most of them, so they swim through the North Sea, and we can't actually, if we catch a fish at some place, we can't be sure that those fish, all the impacts they have and all the impairments, are because of the area we caught the fish in. So we need some stationary fish, and therefore we choose the common depth, Limanda, which does not migrate over long distances, even for spawning. So they are stationary, and they do have a life expectancy up to several years. I think the oldest one caught was 12 years, so we are able to use them as an indicator for long-term effects of diminution. And we caught the fish as close as possible to the wreck. We tried to get at least 50 fish per wreck and then dissected them directly on board. First, we searched the liver for alterations, and then afterwards froze the samples, the tissue samples, for further investigation. And I think it is necessary to also mention we took, from the skull, we took otoliths, so we can actually make an estimation about the age, and our colleagues from the Thun Institute in Bremerhaven did this for us, so we can actually be sure that almost all fish we caught and we choose for the further analysis were between 3 and 4 years, so they're basically almost the same age. So we can even compare them, and we choose the same biomarker. So here's the enzyme activity. It's kind of the same picture as in the with the mussels. We do have a higher catalase activity in fish from the reference site compared to the fish from the rec site. The GST is also a bit higher, but this one is, I can't actually tell why there's a difference. I just need to see. And then for the metabolic end products, it's also the same as in the mussels. We do have the complete opposite compared to the enzyme activity. We have the higher accumulation of metabolic end products in the liver tissue of the fish caught at the rec sites compared to the fish at the reference site. I think it's important to mention because the SMS minus is quite low and even lower than the reference. But as we can see, we don't even reach the limit of detection of TNT in the sediment. And for water, we actually needed a passive sampler because the limit of detection just from the water was too low. So the concentration of TNT around the SMS mines is just quite low. So we also looked at the lysosomal membrane stability, which is able, we can use it to give an information about cell damage and the ability of a cell to protect itself. And in comparison to the results before, this one actually it's worse if you have a lower box plot compared to the higher ones. So as we can see, it in all wrecks, also in all fish caught at the wreck site, it does take a shorter amount of time to break down the membrane of the fish. And now to the really interesting part, we did liver alterations. We divided them in fatty liver, nodules, and swollen liver. And what you can see that especially the severe liver alterations, such as nodules and swollen liver, are insanely high at fish caught at the wreck site. Especially if you look at the SMS Ariadne, because almost 65% of the fish we caught had nodules or even completely developed tumors. And I think it's also important to mention because we also dissected even smaller fish, which were not important for the biological analysis afterwards, but for the chemical analysis, for example, and even the smaller fish, so they are younger, up to 1 year or something, and they also had liver alterations at the SMS Ariadne. And I know I can tell actually all about the results we gathered, but I think it's also important to see if there's actually TNT in the fish. Can we actually see, okay, there is something? And I think all those pictures Edmund already showed, but I think it's important to mention that in all those fish where we can see severe liver alterations, we can also see TNT in the fillet, and it's especially dramatic at the SMS Ariadne. Yes, so as a conclusion, this goes for fish and mussels. We do see alterations in the detox and oxidative stress defense enzyme activities, but they are downregulated. We do see a polluted-induced metabolic disturbance in fish and mussel caught at direct sites. This one only is for the fish part, but we do see an increased number of liver alterations in fish caught at direct sites, and all those results correlate with the emissions of munition around the wrecks. So we can say that war wrecks are a point source for pollutants like dissolving explosive, and their introducing into the marine system impairs the environment and marine organisms, and therefore we need to do something about it. Yes.
There's one thing I take away, it is the phrase insanely high.
Oh, I'm sorry.
I think it captures brilliantly, the situation that confronts us. So we have time for one or two quick questions. Are there any questions? Yes, please. Ben.
Thank you. I think it's to all the speakers. I could understand clearly that the mussels showed a gradient from nothing to concern. And I could see the time series was quite long to demonstrate that. I couldn't quite understand where we think the fish are on that gradient from nothing to concern. Because I guess we're looking at a much shorter time series of samples for the fish fillets. Yeah, for the fish. So for the mussels, you had quite a long time series. And that showed a gradient from 0 to concern. For the fish, I couldn't quite understand where you think the fish are on that gradient from nothing to concern.
Unfortunately, we do not have fish from starting from 84.
Oh, sorry. Apologies.
So unfortunately, we do not have fish to investigate from this 1984, 1805 until today. So the fish which we caught is the fish that is actually living there. And so it is not possible to make a time series, which would be, of course, very interesting, yes.
Great. An excellent question. And we will actually move on now, though, and I would encourage colleagues to contact by email the speakers who have given excellent presentations. Our next speaker is Justin Gwynn. The topic from the Cold War to the present day, the legacy of sunken nuclear submarine Konsomolets. Justin Gwynn is a senior scientist for Norwegian Radiation Nuclear Safety Authority with a focus on marine radioactive contamination issues. His professional appointments include leading the OSPAR Commission's Radioactive Substances Committee and membership of the Hinkley Point C Stakeholder Reference Group. He currently holds an IAEA coordinated research project on global assessment of the levels and impacts of radioactivity in the marine environment.
Okay, before I start, I'd just like to acknowledge my co-authors on this work. And I'll try and work out what is forward on this. Oh, no. Okay, so Konsomolets. So this was a Soviet nuclear-powered attack submarine. Okay, it had an outer and inner pressure hull that was made of a titanium alloy that allowed it to dive deeper than any other submarine of its time. Now, this sank in 1989 following a fire, and it was reported that the nuclear reactor was put into shutdown before the submarine sank, and that Konsomolets was carrying 2 nuclear warheads in its torpedo compartment. We should never forget, really, that the story of Konsomolets is one of a human tragedy, because of the 69 men who were on board, only 27 survived the accident. Today, Konsomolets lies in the Norwegian Sea at a depth of about 1,700 meters. So we have an idea of how much activity was in the reactor at the time the submarine sank, and we also have an idea of how much plutonium was contained within these 2 nuclear warheads. Now, if we fast forward 30 years, a lot of the activity in the reactor has decayed away, and what is left now is mainly due to 2 radionuclides, okay, cesium-137 and strontium-90. And based on reactor physics, we can predict that the ratio of these 2 radionuclides in a reactor should be approximately 1:1. Now, shortly after the sinking, so there were Soviet and Russian investigations of Konsomolets using manned Mir submersibles. And they very quickly detected that there were some releases of radionuclides coming from the reactor in a ventilation pipe at the back of the sail or the tower of the submarine. And this basically implied that the reactor had been damaged. Okay, and this probably occurred when Konsomolets actually sank or when it hit the sea floor. Now, back in 2019, we had a Norwegian expedition, a special one, to Konsomolets. And key to this expedition was the use of this deep-sea ROV, which allows us to carry out high-resolution side-scan sonar, video surveys, but also to allow us the collection of samples at specific points very close to the submarine itself. Oh, I need to go back one. Okay. And that's not spinning around. That's okay. Let's just go this way. Okay, we'll try one more time forward. There we go. Okay, so what you're seeing here now is a model of consomelates on the seafloor based on the side scan sonar on the video survey. And what we see is that at the rear of the submarine, we don't really see much damage at all, but the forward section has a lot of damage, especially in the torpedo compartment. This hole here in the sail, this is where the escape capsule was housed, okay, and this was released when consomelate sank because there were actually 5 crew members still on board the submarine when it sank. Now, in the 1990s, a lot of Russian scientists were very concerned about what was going to happen with the plutonium in these 2 warheads and that plutonium would spread out within the marine environment. So the Russians carried out some work to actually sort of block and to cover up holes and cracks in the torpedo compartment, as well as to plug the torpedo tube holes. And the idea here was that this would reduce the flow of seawater through the torpedo compartment, and also reduce any sort of dispersion of plutonium from these 2 warheads. So one of the first questions we wanted to ask was, okay, has there been any release of this warhead plutonium? And here we can make use of the fact that different sources of plutonium, okay, have different atomic ratios of 2 key isotopes of plutonium, plutonium-240 and plutonium-239. So we know, for example, from global fallout, from nuclear weapon testing, okay, so this ratio should be around about 0.18. But in weapons-grade plutonium, this ratio is an order of magnitude lower. Okay, so when we analyze sediment from around the torpedo compartment, we only actually saw ratios which were sort of more similar to global fallout. And this actually is in line with previous results published by Russia and Norway. And indeed, actually, the levels of plutonium in the sediment around the torpedo compartment are actually lower than what we would expect in that area from other sources of contamination, which is global fallout and nuclear reprocessing. And this is probably because the surface sediment next to the submarine was disturbed when the submarine itself crashed into the sea floor. So we see no evidence for any release of plutonium from these warheads. Okay, so the next question, are releases still occurring from the reactor? Well, on the first dive, okay, we were collecting water samples. This is this ventilation pipe here. Okay, we're collecting water samples from there. We saw no elevated levels of cesium-137 and strontium-90 in these samples. So on this basis, we were thinking, oh, maybe the releases have stopped. Okay, but on the next 3 dives, we actually saw something coming out of the ventilation pipe, okay? And when we took samples from this, we did see elevated levels of these 2 key radionuclides. Again, the highest values here were 800,000 and 400,000 times higher than we would typically see in the Norwegian Sea, okay? The background levels of these radionuclides, okay? But we took another samples a little bit further away, and we could see that these releases actually, the levels decreased quite rapidly around the release point. Now, interestingly, the ratio of cesium to strontium in these releases is about 2 to 1, okay? Rather than the predicted value of 1 to 1. And this probably sort of reflects, when we have some experimental data that shows that cesium actually can leach out of nuclear fuel at a faster rate than strontium-90. So the next question was, can we detect any indications of fuel corrosion? Okay, and again, we go back to this using these atomic ratios from plutonium. I'll just remind you, so global fallout was about 0.18. And we have an estimate for this type of submarine reactor. It's a bit lower, about 0.13. Now, plutonium in seawater has quite complex chemistry. Okay, so we need to look at what's in the dissolved fraction and what's in the solid fraction. And in this case, both of these ratios are more similar to what we would expect to see for a submarine reactor than global fallout. And in addition, we saw elevated levels of plutonium in these samples, okay, far higher than we would expect to see in background water, in bottom water in that area. We also saw increased levels of another radionuclide, uranium-236, in the same samples. And this is also an indicator of nuclear fuel. So based on all these results, we can say that the nuclear fuel in the reactor is starting to corrode. I think the new batteries in your thing. Okay, in the near environment around the submarine, okay, so we do see evidence of a low but an increasing flux of cesium-137 to sediments over the last 30 years. We don't see any accumulation of plutonium in the sediments around the submarine, but we do see a low flux of this other isotope, other radionuclide, uranium-236. Now, the submarine is completely covered by biota. We took some of these samples, and we do see levels of cesium-137 in this biota. Okay, these are low levels, but they are higher than we would expect to see in the same biota anywhere else in the Norwegian Sea. And so this probably does reflect releases coming from the reactor. Okay, just to summarize here now. So the values that we saw for cesium-137 in these releases, okay, so they are within the range of values that were reported previously by Soviet and Russian expeditions, okay? And we do not expect, okay, that these releases will have any consequences for the wider marine environment, okay? And this is mainly due to the depth at which consomnolitz lies, okay? Now, this is supported by all the data we have in the near environment, but also, we expect to say from the data we see quite a rapid dilution of these releases in the surrounding water masses. And also, we can expect that this reactor has been leaking now for 30 years, okay, since it sank in 1989, and we have never seen any unexpected values in any environmental sample that we have taken as part of our regular national monitoring programs of the Norwegian Sea. The releases, they do appear to vary in intensity over time. We do not know why. Okay, and we do not know why we see this visible release either. Okay, so it's not easy, I would say, to observe, and it's not cheap to go and do this work, okay? But consomnolitz, okay, does provide a very unique opportunity, okay, whereby we can understand what is the impact of a reactor that has been exposed to seawater. Okay, so this is something that we've been working on, and we're also very aware of other possible accidents involving nuclear-powered vessels. Okay. Thank you very much.
Thank you. So if we could now please have Dr. John Ash on stage, and we will have time for 5 minutes questions afterwards.
Okay, yep.
That was brilliant. Thank you. Yep. Okay, so Dr. John Ash's presentation will be Cold Water Legacy, Lessons from the Cambridge Northern Seas Radionuclide Project. Dr. John Ash is a former Royal Navy oceanographer and submariner who was involved in the collection of data in the Arctic Ocean to support the study of polar ice pack thinning. He was selected to lead a team of Russian researchers examining radionuclide pollution in the Northern Seas, and was later assigned to undertake the initial design work for the Navy Department's Environmental Management System. Dr. Ash has held a British Safety Council Fellowship at the Judge Institute of Management Studies at the University of Cambridge, and is an associate of the Scott Polar Research Institute, and may I note, has made significant contributions with research and teaching here at UAT. John.
Can you hear me? It's on, is it? Can I just test this also? Is that the laser? Right. And let's just forward. Ladies and gentlemen, as you can see, I've got quite a lot of material to cover, so if you just follow my laser, I'll point out to you the things which are particularly important. I'll guide your eyes. The first disclosure that there was an issue here came in 1991, where a local politician in the Murmansk region produced at a Greenpeace conference a map of dump sites. This outraged delegates at the Consultative Party meeting shortly after that for the London Convention. And it was demanded of the Russians that they produce more information. President Yeltsin was encouraged to do so and appointed Alexei Yablokov to make this study. Let's just remind ourselves briefly about what we know about radiation. There are 3 types of radiation which are of concern here. The first is alpha particles, basically helium nuclei. Secondly, beta, high-energy electrons, and then gamma rays, electromagnetic radiation, but you'll notice that the ionization ability of these 3 types of radiation is inversely proportional to the penetrating capacity. And different nuclides emit different types of radiation. We're interested here, in particular, in strontium-90, cesium-137, and also uranium and plutonium. And you'll notice the half-lives can be extreme, some 30 years when we're talking about strontium-90. But if you start looking down at this part of the table, we're getting into thousands of years. So this is a persistent problem. Yablokov's report was quite extensive. There was some rumor that in fact it had been redacted before I had an opportunity to print it, but that was part of the material, not all of the material that I used in my study. And other material was derived from an American modeling study of the reactors from Lawrence Livermore. You'll notice that there are a variety of different types of entry passage for radiation, including atmospheric fallout. There are about 130 nuclear weapon tests in this area. River runoff, advection of the Gulf Stream, so Sellafield and Kepler Haag would have made a contribution here, and that would have been advected on the Norwegian current. But I was particularly interested in this, which is the disposal of solid waste, including waste that was disposed of with the nuclear fuel still intact in it. And as you can see, there were some major issues here. Part of the problem was there was a concern that the structures that were left might not be left for very much longer. These are buoyancy aids. The whole thing is losing its buoyancy. And there were over 100 of these. That's in addition to what they had managed to dispose of at sea. I was appointed, following the intervention of the First Sea Lord, to a Cambridge group, the Global Security Programme, to try and identify what the issues were and the risk was associated with this. I was aided in my endeavour by 2 Russian scientists who were appointed by Moscow State, but in fact they were paid for through the UK Foreign Commandant's Office. I undertook a literature search, and as I've mentioned, Lawrence Livermore did the reactor modelling. There we are. I approached NRPB, National Radiological Protection Board, in order to give me an authoritative model for risk associated with this, and that they did. And I looked not only at the dose effects, but also what you might be able to do in solution of the problem. So this is, if you like, an inside look in a government study of this and how decisions are made in government. Please don't panic. If you take the activity level and multiply it by this factor here, which is concentration factor there for fish, you end up, ton for ton, with a figure for the amount of radiation per metric ton of fish. If you then multiply that up again by the average harvest, the residence time of the water, and the effective dose per unit intake, what you end up with is a total amount of absorbed radiation, that is to say, per sievert. And that will give you an indication of how many individuals are likely to suffer either fatal cancers or genetic damage. I undertook this calculation using the information provided to me, and the answer was 8.819, which is 1 order of magnitude above a previous American study, which had initially dismissed the whole problem. Nonetheless, when I called NRPB and said, I have found a signal, they said, come and see us tomorrow, which I did, and they checked my maths. The maths was right. Unfortunately, it's not the end of the problem, because if you then take into account all of the additional submarines which have to be disposed of, you end up with a number of casualties which is very much greater. So clearly, there was a need to take some kind of action. What could you do? Well, there are a number of options, and I looked at all of these. First of all, there's the do-nothing option. Now, you've got to include that if you're dealing with a government study. You've got no option. Because the first thing the minister is going to say is, well, what if I just ignore this? He's also going to be interested in trying to identify, well, how much to fix it and who will pay. But if you look at this, do nothing, do little, if you like, do nothing other than inspect, apply extra containment either to the reactors as they become a threat or as their contents become additional threats, and you regulate that by the type of source you believe to be there. Or you could put extra containment on all the reactors. Or you could raise some of the reactors, applying extra containment as required, or retain or raise all the reactors. Now, this is fairly typical government thinking. What are the issues? Do nothing is unacceptable. And it may increase the risk, because if inaction is taken as a precedent, it gets worse. Doing nothing other than inspection, I'm afraid that's effectively the same as doing nothing and it wastes your inspection cost. Similarly, if you're talking about extra containment options, that might be as costly as salvage, and you might still end up with inspection costs. What about raising the reactors? Well, I looked at that option, and I went to a salvage expert and looked at what it would cost, and the answer, as you can see in 93 pounds, was just over 5 million, 5.7 million. If you apply inflation, it's well over 12.1 million now, and frankly, it would be more than that. But that will give you an indication of what it would cost you to deal with that now. What progress has been made? Well, we just had a presentation on the mic. I will look at this as a separate problem. The mic really is two problems. It's the reactor and it's the nuclear torpedoes. The view I took then is that trying to do something about the reactor would be extremely difficult and very expensive. Really, there are very few precedents for it. Howard Hughes actually was involved in one of them, Project Jennifer. It would cost an insane amount of money. However, retrieving the two nuclear torpedoes, so that is the that was the activity level for those, and as you can see, it's plutonium largely there. That is possible, and it's something which I felt should be considered. No, I'm sorry. How do I go back? There we are. So, NGOs were critical in looking at this whole process. It's also important to see that there was a great deal of international activity. A great deal of money was provided by the G8, and unfortunately that funding is now disintegrated because of the Ukraine situation. However, European money has still come forward, and a great deal of progress has been made. So, what have we achieved over 25 years? Well, effectively, we've dealt with everything that was easy to deal with, and this gives you an idea of the containment that's now been provided. The sunken nuclear reactors remain there, and it would be very expensive to deal with them. What have I learned from this whole structure? I'll move on to that later. I've run out of time now, and this has failed now. All right. Major environmental risks rapidly become political issues, and that's true of anything, any major environmental risk. You need a champion, both inside the organization, inside government, and outside, which is why you need the NGOs. The source term is critical, and you need to verify the provenance, and you need to check the maths. I found some errors in the American maths, and I had my maths checked. You need to check the dose effect calculations. Casualty numbers are significant, but you can't really tell at what level government will react. That's difficult to try and predict. But finally, much may be achieved, and we have already achieved a great deal in solving this particular problem. Ladies and gentlemen, I hope that was of interest. Do please let me have any questions that you have.
So, if I may acknowledge all of the speakers for giving brilliant presentations, and also acknowledge too the complexity of the topics they deal with and the way in which, in the brevity of this format, they have managed to squeeze things in. So on behalf of us all here, thank you so much, and recognizing that you do have a huge amount more that you can share, both in the Q&A now and in online and in future. So we do have time for a couple of questions before our session ends. Who has a question, please?
Hi, John. Thank you very much for the scary but very clear information that you gave. I was looking at those great big red things, just assuming because they were big and red, that they were thick enough to protect us from whatever is inside. But how long does it have to be inside? Is it forever? And if it's forever, how do we tell the next generation and the next generation who have to become the stewards?
Fascinating. I'll say a couple of things. The first is that what you're looking at there, those drums, can we pull that back? Is it possible to see that again, please? Those large containment cylinders, if you will. Basically with the reactor compartment of a submarine, and some of the submarines have more than one reactor. So what you can do is you can cut out the midsection of the submarine. You can cut out the reactor compartment. Now that already has containment within that containment. It's also got some shielding. And what the Russians did in many cases was they just filled it with a resonating material called furfural, and then they just dumped it in the sea. With these, generally speaking, most of the fuel would have been removed. It may not always have been the case, and the reason for that is you might not be able to get it out. And if you did try, you would expose a lot of people. Those are issues there. I'm afraid the half-lives dictate, and it's not just the half-lives of any fuel that remains, but also of the activation products in the metal of which the reactor is made. The half-life dictates how long you actually have to deal with this. And I refer you to the work of Thomas Sebiok, who published a very interesting paper on how you would communicate literally down through centuries, and it's extremely difficult to do, because languages, generally speaking, modify at a fairly rapid rate, and they don't really persist. There are some fairly ancient languages, Latin, Hebrew, certainly. The most constructive suggestion for trying to protect this sort of material was to have a kind of an atomic priesthood, that is to say, a group of experts who would pass their knowledge down through the generations and warn our descendants. Because generally speaking, every time we have tried to warn people from digging into things, they have entirely ignored us. I mean, if you think about on one ancient Egyptian tomb, and this is, I think, ideal for this, there was a curse. He shall have no heirs. In other words, he shall become impotent. If he dares to enter the tomb, well, of course, they just drilled straight in the tomb. They didn't care. The grave robbers, I mean, they want money, don't they? So looking at this, given human curiosity and the problems that you have with these sorts of structures, as opposed to other forms of radioactive material which is left over, legacy waste, that kind of thing, this might be the best that we can do. And just try and keep the warning going down through the generations. But I'm afraid the half-lives are, as well, I gave you a table of half-lives. It's frightening.
Right. Could I just, that was an excellent answer, thank you. Could I just ask, is there a question related to the Remarco colleagues and including our colleagues who are online? Could we please have or is that a no scratch?
It's a no scratch.
Okay. No problem. So, colleagues, we have concluded another fascinating session, and may I ask you to show your appreciation to all of the presenters.
Well done, John.